Hi everybody, I'm Josh Redstone.
Welcome back to my channel where I am presently bringing my remaining lectures online in light of the COVID-19 situation here in Canada. I hope you're all doing well. I hope you all continue to hang in there. So thanks for joining me, firstly to all my students and for anyone else who might be watching. Today I'm picking up where I left off on my last lecture, which was all about the neural correlates of consciousness. And if you remember, neural correlates of consciousness are events in the brain, so they're physical brain states that correspond to subjective conscious experiences. These physical events, these brain states, may be particular groups of neurons, maybe small neural networks or larger areas of particular cortices in the brain, or perhaps cortical columns, or perhaps thalamocortical or cortical loops. But in any event, these physical events are taken to correspond to subjective conscious events, and it is thought by some that by identifying the neural correlates of consciousness, we could learn something more about how consciousness is realized within the brain. And of course, last time we talked about the question of correlation and causation, right? Just because we identify a correlation, that does not mean, or that does not necessarily imply, that there is a causal relationship, say, between brain event A and conscious experience B. Nonetheless, we're trying to be objective here. We want to supplement our philosophical theorizing about the brain with objective empirical measures whenever possible. So if we're going to try to identify neural correlates of consciousness, we should keep this in mind, but we should not be afraid. Keep in mind, I mean to say, the caution about causation, correlation and causation. But we should also not be afraid to search for these things. We could learn a lot more about what we're looking for by looking for it, in the case of the neural correlates of consciousness. So last time I also discussed the example of Leibniz's mill. That is, of course, related to the mind-body interaction problem. It's a classic problem in philosophy of mind. And of course, the hard problem of consciousness, which is the question of how subjective conscious states arise from physical states in the brain. Now, we talked about a number of different ways that we could identify possible candidates for neural correlates of consciousness. One of those was studying unconscious brains and comparing them to conscious brains using functional neuroimaging. So here we would ask, what can we learn about the neural correlates of consciousness by studying people in comas, in persistent vegetative states, in cases of locked-in syndrome? What can sleep and dreaming tell us about the neural correlates of consciousness when we examine brains of people who are dreaming or in a coma or in a persistent vegetative state and compare those with the brains of waking subjects? What can anesthesia tell us about the neural correlates of consciousness? And a lot of these, if you remember from last time, seem to point towards the importance of the thalamus and thalamocortical loops. So that is the thalamus, which is quite deep within the brain, serves as a kind of relay for different for information coming from our sensory processing systems or our perceptual systems. Of course, we can take a more specific approach than this, and instead of asking about the neural correlates of conscious in general, or neural correlates of consciousness in general, we can focus on a particular kind of conscious experience. And that's the approach that was taken by Francis Crick and Christoph Koch. Of course, their approach was to focus on conscious visual experience. Consider what happens when you look at a Necker cube. So a Necker cube is an ambiguous figure that appears to flip between two different orientations when one stares at it. I'll put an image of a Necker cube in this video here so that everyone can have an idea what I'm talking about, or refer to my slides or simply Google Necker cube and you'll get the idea. But when you stare at this cube, you notice that the orientation of the cube seems to flip back and forth such that the front and back of the cube seems to shift as one stares at it. And that's why it's called an example of an ambiguous figure. So these perceived changes in the orientation of the cube is a case of visual rivalry. Sometimes this flip is called a Gestalt shift, and that's an idea from Gestalt psychology. And one of the ideas in Gestalt psychology is that consciousness has layers to it. So this flipping or Gestalt shift is something we see when we look at a Necker cube. And we can ask ourselves, do these two different perceived orientations of the cube compete for consciousness? That is one orientation in consciousness and the other isn't, and it's trying to get into consciousness and it's knocking the other perception out of consciousness? We could ask that question, what this flip or this Gestalt shift is really all about. And we can ask this about other cases of visual rivalry too, in particular binocular rivalry. So in cases of binocular rivalry, what happens is two different images are presented to each eye. This could be done by presenting them on a screen very close to one's face, or perhaps with stereoscopic glasses. But similar to what happens with viewing the Necker cube, both orientations of the cube, or both images, in cases of binocular rivalry, seem to compete for consciousness in the sense that we only perceive one image at a time. The images are not combined together into some weird amorphous visual stimulus. If we have two different images in each eye, we perceive one image at a time, but our perception flips back and forth between each image. So, how can we explain cases of rivalry, such as the ambiguous orientation, this flipping back and forth of orientation in the case of the Necker cube, or this flipping in case of binocular rivalry? Well, one early suggestion for explaining binocular rivalry in particular was that this flipping was actually due to eye movements. So perhaps the image flips if we move our eyes slightly, subtly, but move them nonetheless. Or perhaps to peripheral effects. Maybe there was something going on in our peripheral vision when the image is flipping, or which causes the image to flip. But neither of these explanations have really held up under experimental scrutiny, which suggests that this flipping is probably occurring not in lower, more fundamental levels of visual information processing. That is to say, not in the primary visual cortex or very low areas of the primary visual cortex like V1, but that it's probably happening in areas higher up in this information processing hierarchy. So that was the hypothesis that emerged after eye movements and certain other peripheral effects were ruled out as the cause of this flipping in cases of binocular rivalry. Okay, but how does all of this relate to understanding subjective conscious experience and the neural correlates of consciousness? Well, just to reiterate, in cases of rivalry like this, one image is conscious at a time, and our consciousness seems to flip back and forth between the two images. So this is a really good opportunity to investigate the relationship, whether it's simply a correlational relationship or a causal relationship, between objective facts about what's going on in the brain and the nervous system, and subjective facts, if indeed you believe there are subjective facts about consciousness, subjective facts about our experience of the rivalry, say consciously perceiving one image and then that perception flipping to another image and then back and forth, so on and so forth. So here we're dealing with objective facts like what kind of sensory information is entering the eye and traveling down the optic nerves, going to the primary visual cortex, and then working its way up this information processing hierarchy. And the subjective facts refer to the Gestalt shift, or this flipping that happens in cases of binocular rivalry, or with the Necker cube. All right, so some of the first neuroscientific research done in this area was conducted by Logothetis and colleagues, starting around the late 80s and continuing through the 90s. And Logothetis and his colleagues performed studies using macaque monkeys. And in a study like this, these macaques will be trained to report an image they are seeing by pulling a lever. So they have this lever, and they'll have an experimental condition where they'll set up some kind of binocular rivalry that's going on for the macaque monkeys, say by presenting different images in each of the macaque's eyes. And the macaque brain is similar enough to the human brain that we can be fairly certain that their experiences here would be reasonably like our own. So, for example, the monkeys in these experiments might be shown a vertical grading in one eye and a horizontal grading in the other eye. Or perhaps they're shown gradings moving in different directions in each eye. And what they're trained to do is pull a lever that indicates what they're seeing. So if they're seeing a vertical grading, so if a vertical grading is presented, for example, to the left eye and a horizontal to the right eye, when their perception flips to the vertical grading, the macaques pull a lever to indicate that to the experimenter. And then when it flips to the horizontal grading, they pull a lever to indicate that it's flipped to that image, so that they can indicate what's going on in their macaque consciousness, right? So Logothetis and his colleagues trained these monkeys to do this, and they recorded their brain activity using single unit recording techniques. And these involve microelectrodes, and it's a very invasive procedure that we cannot usually perform on people, but this kind of experiment is done fairly often with animals like monkeys. And it allows us to see what's going on at the level of the individual neuron, or very, very small groups of neurons. So these single unit recordings were done using these microelectrodes, and the experimenters searched for brain areas in the macaque's brain where activity seemed to correspond to the changing perceptions. That is, the perceptions, the flips or the gestalt shifts that the macaques were reporting by pulling and pushing these levers. So they were looking for brain areas where the activity corresponded with subjective experience, but not to the unchanging visual inputs to each eye. So they weren't looking for anything that was going on that correlated just with what the eyes were receiving, because each eye is receiving some visual information. They were looking for something that corresponded to the flip, as it were. So what they found was that cells in the early visual cortex, so areas like V1, responded to unchanging visual input. So if I have a horizontal grading in my right eye and a vertical grading in my left eye, well, the cells in V1 will respond pretty much the same. Now, certain cells respond to vertical stripes, some to horizontal stripes. Some cells fire when there's motion versus when there's no motion. But the activity of these cells did not change when the macaques indicated that their conscious experience changed. So in other words, the cellular activity in area V1 in the visual cortex, which is located in your occipital lobes and also in the occipital lobes of the macaque monkeys, the activity of these cells did not change when their conscious experience changed. However, further up the visual pathway, for example in the middle temporal area, or area MT, or in area V4, some of the neurons in those areas' activity changed in a way that apparently corresponded to the flipping that the macaque monkeys were reporting with their lever pulls. In the inferior temporal cortex, for example, almost all of the cells' activity changed in response to what the monkeys were reporting seeing with their lever pulls. So it seems that the neural activity in this area, that is in the inferior temporal cortex, corresponded to what the monkey was consciously seeing in these experiments. So, do the neural correlates of conscious visual experience therefore lie in the inferior temporal cortex, or area IT? Well, there's a couple things we need to keep in mind, depending on how we're thinking of answering. If we answer yes, well, that answer turns on the assumption that macaques' perceptions are, in fact, conscious in the same ways that ours are. And as we'll see later on, some thinkers think that animals are not conscious in the same way that we are because consciousness requires a self, which some thinkers think animals do not have. There's no self realized in the brain in the same way that there is in the human brain. However, it does seem reasonable to assume that macaque perceptions in terms of how conscious they are similar enough to us that these experimental results are reliable. And that is, of course, because we share a fairly recent, we share a quite significant amount of common ancestry with these animals. So our brains are actually a lot like macaque brains. Then again, some other thinkers argue that language is necessary for consciousness, and they might argue that the macaques' responses here tell us nothing about the neural correlates of consciousness, because obviously macaque monkeys don't have language. So therefore their responses, together with the neuroimaging recordings that were done in these experiments, don't tell us anything about the neural correlates of visual experience. Now, we can't really use single unit recording in humans. Indeed, many people argue that we shouldn't use such invasive techniques on mammals like monkeys and apes, which are very similar to us. But thankfully, advances in functional neuroimaging mean that we can now carry out equivalent experiments with people. So let's take a look at those next. All right, so Loomer and colleagues used functional magnetic resonance imaging to see what was going on in people's brains, in humans' brains rather than monkeys' brains, during cases of binocular rivalry. So what happened here was that their participants would wear these stereoscopic glasses, which would present two different images in each eye. In one eye, they were presented with a red drifting grading pattern, and in the other eye, they were presented with a green face. And the participants had to press a key to indicate to the experimenters which image they were consciously seeing. Excuse me. Now, these experimental stimuli, that is the red drifting grading on the one hand, or in the one eye, and the green face on the other, or in the other eye, were different enough that these experimenters could investigate activity in very specialized brain areas. For example, brain areas that are particularly active when we perceive color, form, and when we perceive faces. So they searched for different brain areas where there was significantly greater activity when the face was being consciously perceived than when the grading was being seen. In other words, when the face was the image that one was conscious of, the experimenters assumed that they would see more activity in areas of the brain that were specialized for perceiving faces. And indeed, that's what happened. When the participants reported that they were consciously perceiving the face, or that they were conscious of the face, the green face, rather than the red grading, the experimenters detected bilateral activity, so activity on both sides of the brain, in occipitotemporal areas of the ventral visual pathway, including parts of the fusiform gyrus. And this is especially interesting because the parts of the fusiform gyrus in question was the fusiform face area. This is an area of the brain that specialized in recognizing patterns, particularly the pattern of a human face, the face of a conspecific, or a member of your own species. But they didn't stop there. They also investigated the flipping itself to see what brain areas are active or were active when a flip occurred. So they recorded a participant's series of key presses. So as the participant was indicating with their key presses which image that they were conscious of, where their consciousness flipped to, they had to indicate, right, what they were seeing for the experimenters using key presses. And the experimenters used that sequence of key presses to play back the images to the participants. And that way, they could compare brain activity for the exact same sequences of images, where in the one condition, the flipping was spontaneous, owing to binocular rivalry, and where in the other condition, it was determined. So only one image was being shown at a time. The difference in neural activity observed between these two conditions should tell the experimenters where the flip or gestalt shift was realized in the brain. And they found a lot of differences in a lot of different areas. They found differences in areas in the parietal cortex and frontal cortex. And of course, these areas are implicated in selective attention, which makes sense. I mean, this is something we would expect to see in an experiment like this. And as in the previous research, the experimenters took this to suggest that conscious visual experience is not correlated to anything that's going on in lower level visual processing, such as in area V1. Rather, they took this to mean that conscious visual experience is correlated with activity that's higher up in this information processing hierarchy. In this case, the aforementioned, fusiform gyrus, occipital temporal areas of the ventral visual stream, or here, activity in the parietal cortex and frontal cortex that is usually associated with selective attention. That is picking out a certain stimulus from amongst many stimuli. So what can we conclude from experiments like these? Well, some, like David Chalmers, describe these brain areas as areas where consciousness is generated. Ramachandran, for example, suggests that these studies might help us to narrow down, quote, those brain processes that are qualia-laden, as opposed to those that are not. Francis Crick and Christoph Koch, along similar lines, say that it is the transient results of the computations which correlate with qualia. Most of the computations leading up to those results are likely to be unconscious. So here they are talking about unconscious computations, lower level processing leading up to processing that eventually becomes conscious. In this case, that would be processing that's higher up in this visual information processing hierarchy. Likewise, Jackendorf thinks that intermediate levels of computation are associated with qualia rather than the absolute lowest or absolute highest levels. So where Crick, Koch, and Jackendorf are both suggesting that it's not, consciousness doesn't happen at the top of the information processing hierarchy, but it happens higher up than the lowest level. So somewhere in the middle, for lack of a better term. And of course, Jesse Prince agrees. He writes that conscious states are attentionally modulated, intermediate level representations. So there's some consensus here among both neuroscientists and philosophers of mind that conscious visual experiences seem to be realized in mid-level mid-level information processing areas of the brain. So that is higher up than lower level stuff like that's going on in the primary visual areas, but then again also not quite at the very top of the hierarchy either, if there is indeed a top to the hierarchy. Then again, problems remain, or even not necessarily problems, but things that we should remain cautious about in our interpretation of these results. So obviously one of those is that these results only provide correlations. There's still a question of the nature of whether these relations are actually causal or not. Of course, some researchers have tried to identify whether there are causal relations here between these conscious visual experiences, which are subjective, and physical events going on in the brain, so patterns of activity, brain states, so on and so forth. So Nancy Canwisher is somebody who's explored ways of finding such causal relations. Afraz and colleagues in a 2006 study similarly trained monkeys, similar to some of our earlier discussed experimental work, trained monkeys to categorize these ambiguous images as either a face or a non-face image. And they would then they would stimulate clusters of neurons in the monkey's ventral visual streams while the monkeys looked at ambiguous images. Now, when the face area was stimulated, the monkeys were more likely to indicate that they had seen a face when presented with an ambiguous image, even though the image was not, in fact, of a face. It was ambiguous. It wasn't clear, or rather, was meant not to be clear what the image was of. So that's very interesting. However, none of these approaches so far has really removed the magic from the so-called magic difference. That is the magic difference between what is conscious and what is not conscious. So these results do not really explain subjectivity. They don't really explain qualia. They do not explain why or how consciousness arises at one level, namely a sort of mid-level of information processing, but not at another, like a much lower one or a much higher one. However, this research does offer a promising start. Then again, depending on your theoretical inclinations, you might think that this whole enterprise of trying to identify neural correlates of visual experience, conscious visual experience, is misconceived. So for my students, if you think back to our in-person lecture on Chapter 6 from Susan Blackmore's textbook, if visual experience really is a grand illusion, and there's no, quote, vivid representation in our brains of the scene directly before us, that is no movie in the brain or theater in the brain, then looking for the neural correlates of such things, of this kind of conscious visual experience, is doomed to fail. It's just a misguided, wrong-headed approach that will never work, because we're not going to find what we're looking for, because what we're looking for is not how conscious visual experience comes to occur in the brain. And the same goes for the search for the neural correlates of the contents of consciousness. So what is in consciousness, what we are conscious of. Those things that, remember we discussed the idea of intentionality, that consciousness or conscious states are always about something or of something, and that intentionality is this kind of aboutness that our conscious states have. Well, this would apply for that search as well. One other approach we might take is to forget the idea of locating where conscious visual experience is happening, and imagine that visual experience, or the quality of conscious visual experience, or indeed any experience, any conscious experience, depends on multiple processes and multiple brain areas working in concert with one another. In other words, a complete integrated brain is needed for the kinds of conscious experiences that people report having. To look for specific areas would be, once again, to commit the mereological fallacy and attribute what we're looking for here, consciousness, to a part of a system rather than the whole system, where consciousness is a result of what's going on in the whole system. And these are where theories like Bernard Bars's global workspace theory or Dan Dennett's theory of multiple drafts start to look more appealing if we take this approach. Those who advocate the extended mind view would take this argument even one step further. They would say that, well, we don't just need to look at particular areas in the brain or particular parts of the brain or kinds of activity, patterns of activity. Those aren't our neural correlates of consciousness. In fact, we don't want to look for neural correlates of consciousness because that's not the whole story. We don't just need a part of the brain. We don't just need an entire brain, but we need a brain in a body, in an organism, in a complex, dynamic environment. We need all of that to explain conscious experience. Now, if you're an extended minder, does that mean that the findings of the studies we've just discussed shouldn't be interesting or useful to you? Absolutely not. They might tell us which brain areas are necessary or perhaps even sufficient for people to have reportable conscious experiences. They just don't indicate that there is a specific location in the brain where it all comes together, or that there are specific areas of the brain that generate qualia, subjective experiences, and so forth, and other areas that do not. So it's still an important part of the story, this sort of research, if you're an extended mind theorist. It's just not the entire story. Hello, so much for conscious visual experience. Oh, hi. Are you going to help me teach? Are you going to help me teach the class? Yeah. Oh, that's great. So much for conscious visual experience. Why don't we talk about something else? Something altogether different. Why don't we talk about pain? So the International Association for the Study of Pain defines pain as, quote, an unpleasant sensory and emotional experience associated with actual or potential damage, or described in terms of such damage. And they add to that, pain is always subjective. So pain might be, like conscious visual experience, a good opportunity to compare what's going on objectively, physically speaking, in the brain and central nervous system with what people are consciously reporting. Pain is always subjective, according to the International Association for the Study of Pain, yet pain also always correlates with neural events. Not necessarily events in the peripheral nervous system, as we'll see, but with pain in brain areas. Or with activity in brain areas. So, when you receive an injury, say, you hit your arm on something, or burn yourself, or cut yourself or something, chemical changes occur in neurons throughout the peripheral nervous system. And these are special unmyelinated neurons called C fibers. Now, typically when we talk about, especially philosophers, when we talk about people being in pain, we like to talk about C fibers firing and this sort of thing. So these pain, or these signals, travel through these C fibers, through the peripheral nervous system to the spinal cord, and from there to the brain stem. And from there they go to the thalamus. No surprise there. Remember, the thalamus is like our perceptual relay center of the brain. It goes to the thalamus, and also to parts of the cortex, like the somatosensory cortex and the anterior cingulate cortex. Now, the correlation between experienced pain, so the subjective element of pain, And neural activity in areas like the somatosensory cortex or the ACC is pretty close. In fact, PET scans and fMRIs reveal that there is greater activation in the anterior cingulate cortex when pain is subjectively rated as being more intense. So the more intense pain feels, or the more intense people report that their pain is, the more activity we would observe in the anterior cingulate cortex were we to examine their brain with functional magnetic resonance imaging or something like that. So that's why pain, similar to conscious vision, offers this a nice opportunity to compare the subjective with the objective, or what is consciously reported versus what is actually going on in the brain and in the nervous system. But again, what does this correlation between reported pain intensity and neural activity actually mean? Does this mean that the neural activity is the cause of the subjective experience of pain? Well, that's certainly one possibility, and I think a lot of people would say that's the most likely possibility. But others might say that the subjective experience of pain causes the neural activity. So perhaps dualists or Mysterians would say that this is what's going on. Or perhaps something else is going on entirely. So perhaps if you're an identity theorist, well, mental states are just brain states. There's no A and B. We can reduce B, our subjective experience, to A, the neural events. But maybe we can get to the bottom of this by asking ourselves a question and doing a little thought experiment. So, everybody watching this, pinch yourself. Not too hard, but pinch yourself. So, okay, I'm going to pinch myself right now. I'm not even going to do it so that it hurts, just so that I can feel a pinch. There it is. I have felt that pinch. Now, ask yourself, where is the pain? If you didn't feel pain, fine. Where is that physical sensation that you're experiencing? Now, common sense would suggest that the pain is in your arm. That's where it seems to be. It seems to be in my arm, if I've pinched myself on the arm. But identity theorists would say that the pain is in your brain, or perhaps in your C fibers, firing away in the way that they do. Dualist would say that the pain is in your mind, and therefore has no location, because if you are like a substance dualist, such as Rene Descartes or somebody like that, you think that the mind is an unextended non-physical substance, so the pain has no location. Likewise, if you're perhaps some kind of property dualist, well, the pain depends on informational properties rather than physical properties, so the pain doesn't really have a location if you're a property dualist, like, say, David Chalmers. But what if you have no arm? Amputees, after all, sometimes experience what's come to be known as phantom pain. Indeed, they can experience phantom limb syndrome, where they have the subjective sense that their amputated limb is still present, even though it's not. And sometimes within the phantom limb, they can experience pain. This is known as phantom pain. So here they're feeling pain in the arm, or whatever appendage we're talking about. They're feeling pain in it, but there's no appendage. So how can the pain be located in your arm or in any other appendage? And just a quick interesting note about phantom pain and phantom limb syndrome. It turns out that when one experiences pain in a phantom limb, it's usually because areas on the somatosensory cortex that would correspond to areas of areas of the skin on the amputated limb are still active. And indeed, sometimes adjacent areas on the somatosensory cortex can take over those areas that were previously occupied by the the inputs from the peripheral nervous system on the amputated limb. So for example, say if I've had my arm amputated, and the area of the somatosensory cortex where those sensations would have been computed by the brain is no longer being used by that limb or the nerves in that limb because it's not there anymore. The areas next to it can take over. So say that the adjacent area on the somatosensory cortex is perhaps the hand that I already have. Well, by stimulating the nerve endings on this hand, I could elicit a sensation in the phantom limb. And that's not because the sensations are actually there in my arms. They are, in fact, in the brain. Well, maybe we can get to the bottom of this by asking another line of questions. So, pain. Pain hurts. Who does pain hurt? Well, pain hurts me. It hurts the experiencer of the pain. So perhaps a self is necessary to experience pain. So consider, for example, what Blackmore and others call a spinal dog. So a dog whose spinal cord has been severed due to injury. If we apply to a stimulus, let's say a mildly painful stimulus to the dog's leg, the dog will not show any signs of pain. It won't whimper or yelp or cry out in pain. But its leg will learn to withdraw automatically from the painful stimulus, almost as if it were some kind of reflex action. And sometimes the same thing occurs in human beings, where if the spinal cord has been, say, severed by injury, when poked in the leg, these people will not report feeling anything, and yet the leg will withdraw from the painful stimulus, even though the person feels no pain. So the spinal cord, at least below the injury, seems to be learning certain responses, and it's learning because these responses would be painful to a person whose spinal cord has not been severed. But they aren't subjectively experienced in the case of the person who's been paralyzed or who's lost feeling due to a spinal cord injury. So we could ask, is it the spinal cord that's feeling the pain? Is that where the pain is happening? That might seem a little bit silly on a first pass. Nonetheless, if you reject the notion that spinal cords can feel pain, you also have to reject the idea that animals with the equivalent of just the spinal cord, so certain invertebrates, can feel pain. And yet we would not be surprised if we saw things like jellyfish withdrawing from painful stimuli. We might even react with sympathy if we saw such a creature behaving this way, but the creature has no brain. So if one of those seems silly and the other doesn't, you need to reevaluate your outlook on where the pain is, whether it's in the brain or the spinal cord or the equivalent thereof, depending on the creature we're talking about. And also, what about learning in pain? Pain is sometimes necessary for certain kinds of learning, like avoidance learning. This is the way we learn to avoid dangerous things, like touching hot stoves or sharp objects. The old saying, you can tell a child not to touch the hot stove, but they're not going to really learn not to do it until they burn themselves for that first time, right? That's avoidance learning. If you say that pain is not necessary for this kind of learning, then there's a worry about epiphenomenalism. That is, pain might be an epiphenomenon. Or maybe this would raise the possibility for you that there are pain-free philosophical zombies, for example, who would learn to avoid painful stimuli because zombies' behavior is indistinguishable from ours in every way. They would learn to do this without experiencing pain, which shouldn't make any sense, especially if you're one of those people who thinks that zombies aren't conceivable, right? So if you say yes, spinal cords can feel pain. Then the isolated spinal cord, that means the spinal cord below injury in cases of spinal dogs or people who have had the spinal cord severed due to injury, then you must grant that that isolated spinal cord is what's feeling the pain. But perhaps the pain that the spinal cord feels, the pain that it's using to learn this kind of avoidance response, this avoidance behavior, when we apply these stimuli to areas of the body below the injury, this kind of pain just might be less complex than pain experienced by the entire organism. Then again, some thinkers, as I mentioned earlier, deny that non-human animals can even experience pain or pleasure. I'm not one of those. Nonetheless, there are those thinkers who deny this, like, for example, MacPhail or Antonio Damasio, who thinks that a self is required in order to have conscious experience of pain. So there are certain neural patterns of activity that are associated with pain, C fibers firing and areas of the somatosensory cortex and the anterior cingulate cortex and so on and so forth. Now these might be necessary for pain, but for Damasio, they are not sufficient for pain. For pain to really be painful, one must know that she is experiencing pain. In other words, one needs a self to experience pain. So Damasio says, knowing that you have pain requires something else that occurs after the neural patterns that correspond to the substrate of pain. Excuse me. The nociceptive signals are displayed in the appropriate areas of the brainstem, thalamus, and cerebral cortex and generate an image of pain, a feeling of pain. He continues, the neural pattern of you knowing, which is really what is required here, is just another name for consciousness. So we need neural patterns to realize the pain and neural patterns that realize a knower of some kind, a self, who knows that she is experiencing pain. And this is how Damasio actually distinguishes between actions that are intentional or self-willed and actions that are automatic, like a reflex. You know, for example, when you withdraw your hand from a burning hot stove before you consciously experience any pain, that's reflexive. It's an automatic response. Here you might have C fibers firing and activity in the somatosensory cortex, but perhaps what you don't have in this case is neural activity underwriting a knowing self, specifically a self that knows that it is experiencing pain. That could be what's happening there. That might explain why you withdraw your hand reflexively from a burning hot stove before you feel any sensation of pain. Now Damasio says these patterns, these pain patterns are displayed. Well, displayed for whom or what? Obviously there's a worry of Cartesian materialism or the Cartesian theater here. But Damasio avoids this worry because these neural patterns are not displayed for a who, but for a what. They're displayed to other brain areas. So here, you know, this is a bit like Bars's global workspace theory, where what eventually becomes conscious is just what is broadcast from the spotlight of attention to other mechanisms in the global workspace. And that's how the conscious experience comes about. So the idea of a display is avoided in theories like this because they treat this display not as a display for someone, not really for a self in the Cartesian sense, but more like a self in the sense that bundle theorists might adhere to. But there are other varieties of theory that avoid this display worry, this Cartesian materialism or Cartesian theater worry, by treating sensing and perceiving as a kind of activity. So it's not like we passively sense the world. Sensing the world is an activity. It's something we actively do. Humphrey, for example, makes this argument. He says that sensory awareness is an activity. We do not have pains, we get to be pained, end quote. So, when I experience pain, according to Humphrey, I'm not passively receiving these pain sensations. Rather, I am the active agent, he says. And he continues, thus the phantasm of pain becomes the sensation of pain. The sensation of pain becomes the experience of actively paining. The activity of paining becomes the activity of reaching out to the body surface in a painy way. Philosophers have a funny way of talking about these kinds of things, I suppose. In any case, Humphreys claims that this makes the hard problem of consciousness, at least with respect to pain and other kinds of sensing and perceiving, a little easier to tackle. Although some others disagree. Now, you may have noticed here that Humphries' theory sounds a little bit like O'Regan's and Noe's sensory motor theory, which we covered in Chapter 6, The Grand Illusion. But it also differs slightly from sensory motor theory. Now, O'Regan and Noe and their sensory motor theory, enactive perception, avoid the worries of Cartesian materialism and the Cartesian theater and dualism and all of that stuff by rejecting the idea that perception consists in representing the world. So they don't just say, oh, all of this is a grand illusion. It's not, there's not really a movie in the head going on or an image being displayed on the screen of the Cartesian theater. No, they go one step further and say that we're not, you know, our representation of the world is not just not rich and detailed. It's not a snapshot of reality. There's not even an inner representation at all. This is captured by the idea that they call the new skepticism. So they reject the idea that perception consists in representing the world at all. But for Humphrey, an experiencer, quote, needs the capacity to form mental representations of the sensory stimulation at the surface of its body and how it feels about it. So where Noe and O'Regan deny that there are such mental representations or that mental representations are like that, Humphrey thinks that we need those kinds of mental representations in order for there to be pain. Now, we still don't know the necessary and sufficient conditions for consciousness after all of this discussion on conscious visual experience and pain, phantom pain, all that stuff. But so far in our discussion of the neural correlates of consciousness, we've learned a little bit about the correlations between brain events and subjective experience, and that's still important. You know, we've learned, for example, that more neural activity in pain centers means more reported subjective conscious pain, more intense pain. So the jury is still out. We're still stuck with trying to solve the hard problem. And even though it sometimes seems like after all of this discussion we haven't really got anywhere when it comes to understanding consciousness, we are nonetheless making progress, bit by bit. This is going to take a long time to figure out. Nonetheless, we need to continue on. One day it might be possible for us to do as Leibniz imagined and walk around inside Leibniz's mill. And as we do so, it may turn out that, unlike what Leibniz supposed, we may indeed be able to point to events in the brain and say, that's where consciousness is occurring. Or it could turn out to be that the extended mind theorists are right, and we need to look at the brain, but also the body and the world. Time will tell. All right, so that's it for the neural correlates of consciousness. So next time, I'm going to be delivering a standalone lecture on dreams and consciousness. Now, Blackmore does discuss dreams in this book. I welcome you to read that chapter if you wish, but I won't be relying exclusively on that chapter. I will share some recommended readings for you in case you want to take a look, but I understand that this is probably, this remains a hectic time for all of you. And I want to lighten the load for you as we come to the end of the term, because I imagine all of you are feeling pretty overwhelmed. I know that I am, and I don't mind saying that. Maybe that will put you a little more at ease, knowing that your instructor is also feeling the pinch, feeling the strain of the times a little bit. So, I just want to say, once again, I hope you're all still hanging in there. I appreciate your continued patience as I try to deliver this material to you online. It has not been easy to do. I'm not set up to do it. Nonetheless, I enjoy doing it. And I hope that you are all finding this helpful. And I hope that even those of you who are watching who are not my students might have also found something interesting here. With that said, I wish you all the best, and I will see you again on our next lecture when I will discuss dreams and consciousness. See you next time.